Hello everyone. Today I'm going to show our presentation, which is on line-separable weighted unit disk coverage and related problems. Before we dive into our research, let's talk about a more broadly problem, which is the geometry coverage problem. Given a set P of n points and a set S of m weighted disks in the plane, compute a subset S prime of disks such that each point is covered by at least one disk of S prime, and the total weight of S prime is minimized. Just like this example, we have 3 disks with each different weight. So we can use the 2 red disks to cover all points, which is the optimal solution because the total weight is minimized. And the problem is known to be a bit hard. In our research, we focus on a specific variant, which is a line-separable unit disk. It requires all points P and the centers of S are separated by line L. So the previously best algorithm presented by the Peterson and Wang in 2021, they solved this problem in the quadratic time, and our result to improve this problem can be solved in a subquadratic time. And for the unweighted case, recently Liu and Wang proposed a near linear algorithm to solve the unweighted case, which is each disk can be regarded as the same weight, and the objective is to find the total number of S prime is minimized. Let's talk about our algorithm description. So we essentially use dynamic programming. So the input, we have a disk of S, where each disk Si has a weight WSI, and the points of P are sorted from left to right as P1 to Pn. So our objective is to find a minimal weight subset delta OPT of S that covers P. So initially we have a cost variable for each disks of S. Then we use the weight as the beginning of the cost, and then we do the dynamic programming for each point from the P1 to Pn. For each point Pi, let's use SPI to find all disks S that covers Pi. Then we want to find the disk whose cost is minimal from the SPI. We can use this cost as the delta I. Then for the disk that is not covered Pi, we just update their cost by using the delta I to plus their weight. Then we prove that value on the return by the algorithm is equal to the delta OPT, which is the optimal solution. After we introduce our algorithm, so it's important to show the correctness of our algorithm. We prove it correct based on it compared to the algorithm proposed by Peterson and Wang. So let's first to introduce their algorithm. So they reduce the problem to an interval coverage problem by projecting all points vertically to the line L. For example, if there is a Pi of point set P, so there must be a PR star on the line L, and all the points P star are sorted from left to right based on their x coordinate. Also, they define maximum sequence PIG. For example, if there is a disk Si cover all points from Pi to PG but doesn't cover Pi minus 1, PG plus 1, then we can say the maximum sequence PIG in the disk Si. So using this method, they project each disk by multiple intervals on line L. For example, S1 can be projected to the S1 star, which is one interval on line L. For the disk S2, we find there's 2 intervals can be projected on line L because PR is not covered by the disk Si. Thus, the Pi star is not covered by the intervals generated from the disk S2. For the S3, disk S3, there's also can be used one interval to represent it. After that, they have a P star and S star. Then they solve the 1D heating set based on these 2 sets. Then they compute the delta I star, which is the minimal total weight of the subset of the segments of S star whose union covers all points of P star from the first to the ith point. After that, they prove that delta n star is equal to delta OPT, which is the optimal solution. And in our algorithm, we compute the delta I, which is the minimal total weight of a subset of disks of S whose union covers all points of P from the point 1 to the point I. Then we prove the delta I equal delta I star by induction. Then we have the delta n is equal delta n star, which means delta n is also a delta OPT. To say our algorithm still can find the optimal solution by retain n. So we describe the correctness of our algorithm by comparing it with the algorithm proposed by Peterson and Wang. We use the induction measure to show that for each step delta I is equal to the delta I star. In this part, we will explain more the differences between the two algorithms, and we'll show why our algorithm can get a better time complexity. So we still use their algorithm, so we can say they explicitly update the cost of all related segments of S star. As we said before, they project each disk to multiple intervals on line L, and then they reduce to the 1D heating set. Then for each segment SG star, they need to use the formula to update the cost of the SG star. So the question is, the number of the S star at most will be n squared time, because each disk can be projected at most n intervals. Then it needs like the quadratic time at least to update these segments. And for us, we implicitly update the cost of all related disks of S star. So we don't deal with the disk one by one or intervals like the maximum sequence as mentioned before one by one. We just to solve this disk in canonical sets. Now for each PI, we don't deal with the ON disk. We just update some small number of the canonical set. Or here we just mention it's the root over square n canonical set, and totally the canonical set need to be updated is less than the quadratic time. That's the difference between the two algorithms. So, and after that, both of these two algorithms are using dynamic programming to find they find the delta I star and we find the delta I. So we can find the only difference is we just process this disk in the canonical set, not the one by one. After we talk about how to prove the correctness of our algorithm and explain the difference between our algorithm and the algorithm proposed by Peterson and Wang, so let's talk about the algorithm implementation. Here actually we transfer our problem to a dual problem by the following setting. So here we have a dual point set Q, which is a set of centers of all disks of S. And we have a dual disk set D, which is a set of a union disks centered at the point of P. Since all the disks in the original problem are union disks, then we can easily to get the dual point set and the dual disk set. Then we transfer our original algorithm to a dual algorithm. Here we only introduce the differences between two algorithms. Still, initially we associate the cost for all dual points Q here instead of the disks. Then we use a dynamic programming to process the disk from D1 to Dn. For example, the Di, let's QDi to represent all dual points in Q that are covered by Di. Then we compute the delta I by finding the point with the minimal cost among all points are covered by DI. And then for the points that are not covered by DI, we up their cost by using the delta I plus their own weight value. Then we can return the delta N. Since all these disks are union disks, then we can transfer the algorithm from the original to dual, which can show the dual algorithm is also correct. The reason we want to use the duality is because instead of processing disks in batch, we can process dual points in batch more easily, and by using the technique and the tools in the later. After we introduce how to transfer our original algorithm to dual algorithm, then we can process points in batches instead of process disk in batches. Then we talk about the techniques that we use to process this point. Let's start with this disk. For each disk DI in D, since its center above L and all points of Q are below L, only the portion of DI below L matters to the dual algorithm. We call the boundary portion of DI below L the lower arc of DI. That actually denotes the set of the lower arcs of all disks of D. Then we use the hierarchical cutting proposed by Wang in 2022. He adapts Chazel's algorithm for halfplanes. To compute it, the cutting on edge will take the ONR time, and each cell produced by the cutting will be a pseudo trapezoid. If we say there is a cell is sigma, then we use A sigma to represent all ancestors of sigma. Since the height of the hierarchical cutting is log r, so the numbers of A sigma is up to log r, which means in each layer it will have an ancestor of sigma. Then we use the C sigma to represent children of sigma. Each sigma has constant children. Besides, we use H sigma to represent arcs of H that intersect sigma. So that for the each cell is at most n divided by r arcs, because we totally have OR square cells. Then there should be a ONR arcs in the whole cutting. Then we process the points. For each point, dual points, we do the point location to see where it's located in the cell of the last level. Since there's OR square cells and we have OM points, each cell in the last layer will have OM divided by R square points. After we introduce the techniques that we're going to use in our dual algorithm, so recall that we have two key operations in our dual algorithm. So in order to handle that two operations, we first perform some pre-processing work before we run the dual algorithm, which is to find for each cell in C, we want to find the minimal cost of all points in this cell. So we discussed a data structure which will be used to support the key operations and to help to find this minimal cost. Then for each point in the Q, we associate with a variable lambda Q. And for each cell in C, we associate with two variables. The first is a minimal cost sigma, just we described earlier, and another one is lambda sigma. So the things that we need to emphasize that all this processing is just for the minimal cost for each sigma. And after we initialize this variable for the point and the cells, then for each point Q in the last layer, which means the C K, then we can find the cost Q is equal this formula, But at the beginning, because all the lambda q and lambda sigma is 0, so the cos q just its own weight. Then for the sigma is a cell of a cassette K, we can simply find the minimal cos sigma by compare all the points in this cell. And for the sigma is the cell not in the cassette K, we just use a bottom-up manner to add this cost, because for each sigma is not in cassette K, it only has constant children, so we just need to compare the minimal cost of its children, then we can find the minimal cost of itself. So after that, we prove the minimum cost for each sigma based on this formula. So that is a pre-processing time, and we show that the pre-processing time takes O(n) log n plus nr plus m log r time. After we talk about the pre-processing part, now let's talk about the algorithm implementation. So we know there are two operations in our algorithm. Let's start from the first one, which is find minimal cost operation. We are computing delta I in terms of di, so which is the minimal cost of all points of Q inside the disk di. And we still use the data structure hierarchical cutting from the previously mentioned. So we find the cell that intersect with the lower arc of di. We say it's sigma, and we use a sigma prime to represent the children cells of the sigma. And we only need to consider about two conditions. The first condition is the cell sigma prime is completely covered by the lower arc of di, and the other one is Q sigma is intersect with the lower arc of the di. And for the cell sigma prime is doesn't intersect at all with the lower arc of di. We don't need to care about it because we know there is no point in that cell is covered by the di. Then let's start from the first condition, that sigma prime of sigma that is fully contained in di, because in the pre-processing part we already find the minimal cost of sigma prime. We only need to check each gamma value, each lambda value of its own ancestors cells. Then we can use the alpha sigma prime to record the minimal cost of all points of sigma prime that covered by disk di. And for the condition that the lower arc intersect with the sigma prime, then we continue to check its children cell until the cell in the cassette K is not fully contained in di, then which is straightforward because we only check the all points that in cassette K that are covered by di, and we use the alpha to record the point with the minimal cost. Then we compare all conditions that we record and to find a point with a minimal cost. So this part takes ONR plus MN divided R and times log R times, because the height of the cassette is log R. After we find a point with a minimal cost among all points covered by di, then we get a delta I. According to the algorithm, now we need to do the reset cost. So we update the cost of the points are not covered by di. We still use the same data structure hierarchical cutting. To see there's actually two conditions that we need to consider. The first one is the lower arc of di that intersect with a cell, and the lower arc of di doesn't have any intersect with a cell. And for the condition that if the cell is completely covered by the lower arc, then we don't need to consider about it, because any point in this cell will covered by di. However, we only update the points that are not covered by DI. That's why we only need to focus on the first two situations. And for each point in this two situations that are not covered by DI, we need to find the location of this point in the cassette K, which is the bottom layer. For example, we use we use a Q to represent the points in the first two situations that are not covered by the DI. So we need to find all the points that are not covered by DI and find this location in the cassette K. Then first thing we need to update the cost of this cost. We just use the Q to represent this point, and based on the formula that we mentioned before, we need to update the lambda Q to get the new cost. Because all the lambda sigma prime, for if the sigma prime is the ancestors cell of the sigma, then the lambda sigma prime doesn't change. Then we sum all this value together to get the lambda Q. After that, we need to update the minimum cost of the sigma because the cost Q is changed. So we have to verify the new minimum cost. So if the sigma is a cell in the cassette K, which is the last layer, the bottom layer, so we just need to compare the cost of the Q with the previous minimum cost to get a new minimum cost for the sigma. And if the sigma is not like in the cassette K, then we can just use the observation that each sigma only have constant childrens. So we use the minimal cost of the children cells to update the sigma. Then it will be from the bottom up manner to update each cell. Then we got the time complexity. Since all the points that need to be updated, we use the Q sigma. Then for each sigma, we need to update log R plus log M time. Now let's talk about the second situation where the cell sigma doesn't have any intersection part with the lower arc of the DI. So this situation is a little bit different with the first one. In the first situation, we don't update the lambda value of the cells. We only update the lambda values of the points because the lower arc of the DI continues to intersect with the cell until to the cassette K. So we just keep the lambda value for all the ancestor cells of the sigma E. But in this condition, this situation is kind of different. It doesn't have an intersection from the sigma. Then we, based on the cos Q equal to a WQ plus delta I, we update the related cells lambda value as following measured. So at first, we summed all the lambda values of the ancestor cells of the sigma. Then we use the delta I minus this value as the value of the lambda sigma. Then for all its descendant cells, we just set the values is equal 0. These two formula can make sure our cos Q is equal to WQ plus delta I. Then we use this measure to update all the points in the sigma. Then the reset operation is bounded by this formula. After we talk about the implementation of the two operations in our algorithm, actually there are three things that need talk about the time analysis. The first is the pre-processing part. In this part, we find the minimum cost for each cells in the cutting, and we associate the lambda value for each cell and the point of Q. And find the minimum cost, which means for each disk DI, we we have to find the point with the minimal cost among all points covered by this disk. And then for the points that not cover this disk, we need to reset their cost. So these 3 steps takes a time analysis by these 3 formulas. Then the overall we have this time complexity. Then by setting r equal to the minimum of the root square m or n, so then we get the time complexity of the overall algorithm. Then we talk about the related problems. So the lower only half-plane coverage can be regarded as a special case of the line-separable unit disk coverage problem. Then we can use the same techniques and time complexity to solve the lower only half-plane coverage problem. Also, the lower only half-plane heating set can be regarded as a dual problem of the lower only half-plane coverage problem. Then our algorithm can improve both these 2 problems. The previous best of these two problems are also quadratic time, and our results can be improve these 2 problems to the subquadratic time. Besides, the Peterson and Wang mentioned the general half-plane coverage can be reduced to O(n) squared lower only half-plane coverage problems. And the Liu and Wang mentioned that general half-plane heating set problem can also be reduced to O(n) squared lower only half-plane heating set. But need to mention that the general half-plane coverage is not the dual problem of the general half-plane heating set problem. Then since we improved the previously best algorithm of the lower only half-plane coverage and heating set problem, then the general half-plane coverage problem and general half-plane heating set problem can also be improved by our algorithm in the line-separable unit disk coverage problem.